All right, good morning, eighth grade science class. Today we're going to be going over the matter and energy vocab just briefly. I'm also going to be sharing my screen and showing you some visuals and audio from a website that we have called STEMscopes. You are able to log into this site. You'll have to get your username and login from me because those have changed this year. But you are able to use this site for reviewing and for using things like the visual glossary. So we're going to be starting on page 6 today. But it's a matter energy vocabulary. And so we're going to be going through these vocabulary words and pulling up some important ones on the screen here, okay? So first we're going to start with our atomic structure, right? Well, atomic structure, the building block of all life is the atom, all right? It makes up everything on our planet, all right? All of our elements, all right, are made up of atoms, all right? So as our first one, atoms are for atomic structure. Right. Then we have our nucleus. The nucleus is the center of an atom, guys. This contains protons and neutrons. Not to get this confused with our unit on cells when we also talk about a nucleus. Nucleus is the brain of the cell. It houses the DNA. It's kind of controls the cell. But when we're talking about atomic structure, we're talking about the center of the cell, what holds the protons and the neutron, what makes up most of our mass. Next, we have our electron cloud. This is where the electrons live. It's outside the nucleus. And because the electrons move around so fast, fluidly, it almost looks like a cloud whenever you look at it. Next, we have protons, neutrons, and electrons. We know these are our 3 subatomic particles. This is going to be our positive, our neutral, and our negative. Our positive and neutral live inside the nucleus, and our negative live in the electron cloud. Now, a type of electron would be a valence electron. These are electrons that live in the outside shell. Whenever we look at a Bohr's model, we can see where the electrons are placed. And a Bohr model will show us how many valence electrons we have. But you can also tell the number of valence electrons based on the group that your element lies in. But valence electrons are just the electrons in the outermost shell. Next, we have the 3 things that show up on the periodic square. The atomic number, which is the number of protons you have, which also equals the number of electrons you have. Then you have atomic mass, which is the number of protons plus the number of neutrons. They do have a little tiny number in there that involves our electrons, but the mass is mostly made of our neutrons and our protons. Then we have our chemical symbol, which is just 1 uppercase letter or 1 uppercase and 1 lowercase letter, but it always is shown on the periodic table and it represents all of our different elements. And then the Bohr models is the way for us to visualize all of this. We call it the Bohr's model because it does look a little boring, but it shows us protons, neutrons, and it shows us the electrons and where they're located in the electron cloud, which energy level or energy shell that they're located on. Remember, only 2 electrons can live in the first shell, 8 electrons in every shell after that. Moving on to the periodic table, we talk about periods and groups. Periods go from left to right on the periodic table. Groups go up and down. The groups are going to show us a couple things. They'll show us valence electrons, while periods show us the number of electron shells or rings that the atom has. When we're talking about reactivity, we're talking about the tendency for an element to react with another element. If you look all the way to the right of the periodic table of group 18, these are known as our noble gases. They don't react with any other element. They only react, they don't react with anybody. They don't even react with themselves. So because they have 8 valence electrons, they're considered as non-reactive. But if you go to the very left side of the periodic table and you look at group 1, you'll see that all of these elements only have 1 valence electron. So other than hydrogen at the very top, the rest of those elements have a lot of room to share, meaning that when they bump up against another element, they're going to grab on to that element's electrons and they're going to hold on to it in their outside shell. And since they only have 1 valence electron, all of them except for hydrogen have about 7 spots to fill in their shell. So it makes them very reactive. So as you move from right, non-reactive, to the left, you become more and more reactive on the periodic table, meaning you're going to react with other elements. Next, we have our alkali metals. These are elements located in group or family 1 on the periodic table. These are metals, but it's going to be located in group 1. Then our alkaline earth metals located in group 2. Transition metals located in everything from 3 to 12. As you can see, most of our periodic table is metal. Then we have our halogens located in group 7. Remember, those are going to be our nonmetals. And then our noble gases, our famous noble gases located in group 18. And that covers our periodic tables. Moving on to page 7, need to know the difference between, ladies and gentlemen, thank you. We need to know the difference between metals, nonmetals, and metalloids, all right? Now, we know that the characteristics of metals, nonmetals, and metalloids, things like luster, being ductile, conductivity, whether or not you're an insulator or not, whether or not you have properties of both. But where these are located on the periodic table is very important. Remember that metals are located on the left side of the stair-step line. Non-metals are located to the right side of their stair-step line, and metalloids are everything touching that stair-step line with the exception of aluminum. It's the only one that's off whenever we use that stair-step line trick, okay? When you're talking about luster, it means light reflecting off it. It means it's shiny. Malleable means that you're able to shape it and reshape it. Think of metal. You can move it into a shape, or aluminum foil, but you can flatten it back out and get it back to how you originally was. Then we have our ductility, which is the ability to be stretched into wire. Only metals have that ability. Brittleness would mean that you break under pressure. You're not going to be malleable. You'll be brittle if you break under pressure, you shatter, you crack, or tear. Next would be conductivity, and this is how energy flows through something. If energy can pass through you, and this means energy like electricity, heat, cold, all right, which is just thermal energy. This conductivity means that energy can pass through you. If you're a conductor, you're a metal, all right? Or you could be a metalloid. If you're a non-conductor, it means you're an insulator. That means you're a non-metal. And that covers all our metals, non-metals, and metalloids. Next, we're becoming elements, compounds, and mixtures. Elements, compounds, and mixtures, guys. Elements are pure, same as compounds, since compounds are just pure elements put together. A compound is 2 or more elements combined. A mixture is just a mixture that's not chemically combined, meaning you can separate it if you needed to. And last but not least, our organic compound. And we memorize the acronym CHOMPS for our organic compound, CHOMPS, and that's carbon, hydrogen, oxygen, phosphorus, sulfur, and nitrogen. So that CHOMPS acronym is just all of the elements that you can find in organic things, living things, but carbon being the most important one. Whenever we went through chemical formulas, we really had 2 big words here, subscript and coefficient. A molecule is just a collection, right, of elements, all right? One molecule of, say, carbon dioxide, CO2, or a molecule of H2O. And sometimes molecules are represented by a coefficient. This is the number in front of an element or compound that indicates how many molecules you have. It's the big number. Then you have your subscript. Those are the small numbers after a chemical formula that tell you exactly how many specific atoms you have of that particular element. If there's no subscript, it means there's just one, okay? Since we understand a chemical formula, then we can start talking about chemical equation. A chemical equation is when you have that arrow right in the middle, and you see the reactants on one side is what you start with on the left side of the arrow, and then you have your products on the right side. That's what you end with in a chemical equation, is your product. And you know that because a chemical reaction has taken place, a chemical change has taken place. There's 2 types of equations, balanced and unbalanced. If the number of atoms and the elements match on both sides of the arrow, you're balanced, you exist. If they don't match, you're called unbalanced. This cannot exist, doesn't exist on our planet. Sometimes the STAR tests like to throw those at you, so you know the difference between unbalanced and balanced. But all this has to do with the law of conservation of mass. Just like the law of conservation of energy, matter cannot be created or destroyed. It's just change. So if you start with 100 grams of something, you have to end with 100 grams of something, okay? You can't create matter out of thin air, okay? One more page on vocab for matter and energy. We have our chemical reactions. Chemical reaction, guys, is anytime a new substance is formed, all right? When a new substance is formed, this is called a chemical change. You no longer have the original substance. A physical change would be the opposite. If you do have the original substance after, it's been a physical change. Did you cut it, break it, smash it, dissolve it? This would be a physical change because if you wanted to, you could get your original substance back. Chemical properties are any properties that identify a substance. Physical properties are characteristics that can be observed or measured. It's the difference between the 2. Chemical properties, all right, chemical properties again can be determined and change in the identity of a substance. So it's characteristics. While physical properties are those things we can observe, actually see, maybe even touch, okay? Evidence of a chemical reaction, we talked about all the different signs of a chemical reaction in our packet, things like production of a gas, precipitate, formation of energy like heat, color change, unexpected color change or temperature change. These are all signs of a chemical change, evidence of a chemical reaction. All right, when we're calculating density, we did our density triangle, right? Density equals mass divided by volume, but mass is just the amount of matter inside of an object, not weight. Weight is different than mass. Weight can be different on planet by planet because weight is a calculation using gravity, right? But mass is how much matter you have. Your mass won't change no matter what planet you're on. Volume is the amount of space something takes up. That's why we're able to use the displacement method down here to figure out our volume. If you place something in a bucket of water, see how much that water rised. That's how much water was displaced. That's the volume of your object. That's the water displacement method here, so we don't have to cover that one, okay? Next, density is just the ratio of an object's mass to its volume. Mass, ladies, almost done here, guys. Mass divided by volume, all right? It's easy to figure out the volume of a regular shaped object, length time width time height, but it's harder to find the volume or density of an irregular shaped object. That's why we have to use a graduated cylinder and the water displacement method. A graduated cylinder is that lab equipment with the numbers on the side, looks like a long tube, all right? And you drop some in there and you can see the water rise, you can see the water displace. Last three for this matter energy vocab section would be the energy flow, a food chain, a food web, and an energy pyramid. A food chain is a simple system. It's a one-way street, starting with the sun and usually ending with some type of consumer, maybe even a predator. But it's a series of events when one organism consumes another organism and energy is passed down. The arrow in both the food web and a food chain is showing which way the energy is flowing. A food web is going to have a lot of food chains kind of overlapping because animals have diverse diet, complex diet, and so an animal will eat multiple things. And you'll be able to see that in a food web, not so much in a food chain. But an energy pyramid is going to show us how the energy is flowing through the system. All energy starts at the bottom, right, with our producers because they're producing all the energy that comes from the sun, that energy that comes from the sun. Then we have consumers, both secondary and primary, all right, producers and consumers with secondary and primary. And then like the top of the chain pyramid, we have like our apex predators, right? Those predators that aren't eaten by anything. That's where the energy stops. But they're not getting all the energy that comes from the sun. As you move up the energy pyramid, you're constantly losing energy because it takes energy to survive, to live, to reproduce, to eat. It takes energy. These animals use some of that energy that they received from the last organism. So by the time you get to the end of your pyramid, you're talking about percentages of energy that's actually reaching the source from the sun. Okay? So that covers our, ladies and gentlemen, that covered our matter and energy vocab. That was page 6, 7, and 8. One thing that you can do, and I'll share my screen real quick with you guys. Hey guys, hold on one sec, guys. Keep it down. I'm almost done. All right. So on STEMscope Speedia, sorry about the share there. I want to try this again. There you go. Share that one. Nope. Right. 1 second, guys. I apologize. All right. So as you can see here, there's a visual glossary on STEMscope Speedia. So if you're having trouble with any of these words and you want to see it, either a picture of it or even watch a quick video of it, then you only have to go to your visual glossary, choose the start. So let's start with, let's just do nucleus, okay? So hit Control F, type in nucleus up at the top, and it'll take you to all the nucleus things here. So as you can see, ladies, gentlemen, please be quiet, almost done. We have our atomic nucleus, right? We're also going to have our nucleus that talks about cells as well, okay? But here you see, you can click here, you can see the visual. Some, I got you. Some show the video as well. So you can use that as one of your resources.